Good job, everybody. Organic Chemistry 1, Chem 230. We made it to the last chapter of this course, which is chapter 10. Chapter 10 is about radical reactions. Radical reactions are a special type of reactions, totally different from the ones that we have learned in the previous chapters. Okay? So radical reactions, as the name says, uses radicals. We will define what a radical is, but we will see that here is not charge driven. Remember in the previous reactions, we were using a plus and a minus, delta plus, delta minus. There's always a polarity that is associated with the reactions that we have seen in the previous chapters. But here in radical reaction, we'll notice that that's not really the driving force. Okay, so just to give you an idea what we'll be dealing with or what we're going to be learning in this particular chapter, here is a brief outline for chapter 10. It looks long. It's a lot of concepts that we're going to be learning, but to be honest, it's not that long, right? So this one is the structure of a radical. This one is what we named radical. As you can see, by definition, a radical would be a species that has an ampere electron. Here you can see that the carbon has no charge. There is no charge for the carbon, but the carbon, let's say like this one is the methyl radical. Methyl radical doesn't exist because it's very unstable, as we will learn later. But this one will be the methyl radical. Carbon has, if you do the formal charge, carbon belongs to group 4A of the periodic table, minus number of electrons that are sitting on the carbon will be 1, 2, 3, and 4. 4 minus 4 will be equal to 0. So this carbon has a 0 charge. So there is no plus, there is no minus. It's totally different from a carbocation. Remember a carbocation that has a plus charge, or a carbon ion. The carbon ion also has a minus charge, right? Carbon and carbocations, they have charges. Radicals do not have charges, but they do have an incomplete octet. You more or less can guess now what is the driving force for radical reactions, right? So we will start with a brief introduction where we find radicals in general, where it is, right? Where do we have radicals in life? Structure, geometry, physical properties, stability of radicals. Then we will learn how resonance, if resonance works in radicals, and how it affects stability. Then we will see the radical reaction patterns, slightly different from regular reaction we have seen. Okay, but here we will learn it. Normally it's divided in 3 steps. Then we will find our first reaction, which is halogenation of alkanes. So here we will work only with alkanes. We haven't seen any reaction of alkanes before, right? So we did substitution with alkyl halides with a leaving group, elimination to produce an alkene, addition to alkenes and alkynes. We haven't done anything with alkanes, right? Reactivity of alkanes. So here is where we will use halogenation of alkanes, right? In the radical reactions to give some functionalities, to give some life to alkanes. Alkanes are pretty much very boring molecules. They're very useful in chemistry, but if you look at that compound, for example, this is butane. Butane has nothing. It's just C, 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 H's everywhere. So what is the special has butane? Nothing. But if you do a radical reaction, you will bring it to life. We will come up with bromobutane. And we know that bromobutane can be used in substitution reaction, elimination reactions, right? Once you produce the alkene, you can do a series of reactions according to chapter 8. And then from alkene, you can go to alkyne. And in alkyne, you can do other reactions that we have studied on chapter 9. Right? So this particular section really opens the door to many reactions that we have studied in the previous chapters. Then halogenation can happen. Halogenation can be fluorination, chlorination, bromination, iodization. But which ones are the most important? The most important are chlorination and bromination. We are going to evaluate what is the difference between chlorination and bromination. Then we will go something very special, which is allylic halogenation. I'll explain you what is an allylic position, and that will be your second reaction. Then is the anti-Markovnikov hydrohalogenation of alkenes. Remember that reaction in which you have an alkene like this, you added HBr. We got the Markovnikov product. But if you had the same reaction, but with HBr peroxides, you were getting the anti-Markovnikov. What is the difference, right? Why the peroxide makes an effect, right? So what is the change of the peroxide? We will explain today why the peroxide That's the anti-Markovnikov addition. Okay, so that is in the second to last topic to cover in this particular chapter. And the last chapter is special, is about radical polymerization, reaction number 4. Radical polymerization is strongly associated with what we know as plastics. Okay, so that's how plastics are made. For example, this particular part of the pen, which is plastic, that is made with by radical polymerization. This one, the case for this corrector, right? So it is a plastic that was done by polymerization of using radicals. Plastic bags, I don't have a plastic bag close to me right now, but definitely those are also made by polymerization of the using radical reaction, right? So let's get started with the first section. So we know that we're working with radicals. So first, let's go back to chapter 6. Remember in chapter 6 that at the very beginning of that chapter, we explained that the chemical reactivity of organic molecules can be divided into two ways how to break, right? How to break bonds. We can do a homolytic cleavage or a heterolytic cleavage. So far we have been doing heterolytic cleavage. Heterolytic cleavage is when you have molecule X and Y, and then Y is more electronegative, so it decides to dissociate and breaks into two ions, right? So that is what we see right here is what we call a heterolytic cleavage, right? One of the two atoms, right? One of the two sharing atoms takes the electrons. That's what we call heterolytic cleavage. But there is another type of cleavage, which is called the homolytic cleavage. So that happens when both atoms, they decide to take each one electron, right? Remember that the covalent bond is formed by two electrons, right? So right here we have 1 and 2 electrons. So they spontaneously decide to separate, and each of them will take their own electron. Now, does it have to be, what happens with the electronegativity? Electronegativity can do something about it. For example, if I have HBr, can I expect these guys to also do a homolytic cleavage? Yes. Okay, so homolytic cleavage can happen in non-polar, right? For example, a CC bond, but can also happen in an HBr bond. Why is that? Why am I bringing up this difference? Is that here there is no difference in electronegativity. Carbon-carbon, there is no difference in electronegativity, but in HBr, there is a difference in electronegativity. So can highly polarized bonds, can they still do homolytic cleavage? Yes, they can also do homolytic cleavage. Why? Because the reaction conditions are different. Okay, what do you mean by reaction conditions? You have to provide the energy to make it happen, the homolytic cleavage. If you don't have the energy, then you have to give it, not necessarily with heat. Right here you see heat, but sometimes can be done with light, UV light, right? So for example, whenever you guys go to the dentist, right? So have you ever tried doing some pasting in your tooth or filling, right? Normally they put like a white, right, substance. It looks like a plaster, right? It goes inside, and then the dentist applies a light. They call it a halogen light, but it's really a UV light. So it has some UV radiation. UV means ultraviolet. So it's a high energy radiation that they apply, not as high as X-rays. X-ray is actually toxic. It's damage your tissue and your DNA. But UV radiation in the long term, yeah, it does produce cancer, but it's not as invasive as X-rays. So they apply that, and then they make it occur like a series of radical reactions inside of that particular composite, right? Composite that which goes inside of your tooth. So that is what happens. So you have to apply energy. You provide the conditions for the homolytic cleavage to occur, it will occur. Right? So in this example, you have X and Y. So X goes with its own electron, and Y goes with its own electron. Something that they highlight in this slide is the way how you are using the arrows. Normally, we've been using this arrow that you see here on the left side, the double arrow, right? What we call a double barred arrow. That is the arrow that we've been using all the time. But for this chapter, whenever you guys are involved in homolytic cleavage, which is all here in chapter 10, we are going to be using the fish hook. Shows the motion of one electron. Well, the rationale behind that is that this arrow, right, that you see at the bottom, it moves two electrons, one here and one here. Those are the two electrons. And in the fish hook, you're only pushing one electron. That's the rationale. I mean, kind of simple, but yeah, they divided the arrow into only one side. So that's why they make it a fish hook, right? So every time you guys see a fish hook, that means that you are involving a radical reaction. Why? Because you're forming radicals. That's what it says here in the main reaction, is that you have a radical here, radical X and radical Y. How do you recognize a radical? Because they have an unpaired electron. It's highly reactive. Because remember that electrons, they like to be paired, because when the electrons are paired, the magnetic field is compensated. Remember that the spin, one rotates clockwise, the other electron rotates counterclockwise. So that's how they compensate the electron-electron repulsion. But when one electron is by itself, there is no compensation of that particular rotation, right? Remember, electrons are always rotating, spinning. That's why there is a spin number, plus 1/2 or minus 1/2. So when the electrons are spinning in only one direction, they compensate that energy from rotation in one direction with the second electron. So if one electron is lacking of a partner, definitely there is an uncompensated force that gives the atom instability. It is unstable. So that forces, that's why they say that radicals are highly, highly, highly reactive, right? So in terms of the physical properties and geometry and stability of the radicals, radicals are also under sp2 hybridization. Okay, so radicals appear to be trigonal planar. Always think of that. So that means that this electron that you see here on the left side, that electron can be here, can be here, can be here, can be here. Anywhere in the p orbital is moving inside of the p orbital, everywhere. That brings one particular issue, that whenever there is a radical reaction, you can have a reaction here, or you can have a reaction here. Okay, so you see the implications, right? So the same way as we were analyzing a carbocation, remember a carbocation that it cannot be attacked from the upper lobe or the bottom lobe. So the same thing happens with the radicals. The radicals are also under sp2, therefore it can be attacked in both sides of the p orbital. Okay, so here it is another way how to represent it. It says like, or a shallow trigonal pyramidal sp3 hybridized. They call it sp3 hybridized because the radical really moves in one direction. That changes the hybridization, but really, really the radicals are thought or are known to be sp2 hybridized. Now, in terms of the stability, there's a stability trend. Radicals see a little bit similar to the carbocation. So the stability of carbocations is strongly associated with the stability of radicals. And you can see that since here, this particular carbon is electron deficient, you can also say that it's electron deficient, even though it doesn't have a plus charge, but it has an unpaired electron. That unpaired electron creates a deficiency in that particular carbon. So as any electron deficiency, it really asks or demands the help of the neighbors. So the more neighbors you have, or the more branches you have, the more stable the carbocation is going to be. For example, methyl radical, which is all the way on the left, there is no help from the hydrogen. Hydrogen has only one electron. So hydrogen doesn't really help you much, right? If you are demanding coverage or shielding from another atom, hydrogen is the worst because hydrogen has no electrons, no core electrons to help. Primary, yes, this R group donates electron density. In a secondary, I have 2 groups donating electron density. And in a tertiary, I have 3 groups donating electron density. So a tertiary radical is more stable than a secondary radical, primary, and then the methyl. You could even say that the methyl radical doesn't exist, it's highly unstable. Secondary and tertiary, they are somewhat stable. Okay, so radicals follow the same stability trend as carbocation. They are both electron deficient, right? So deficient, there is electron deficiency, not really a charge, but there is a deficiency. And the deficiency is created because of the incomplete octet, right? The carbon doesn't have the 8 electrons. So that electron that is unpaired demands the presence of a partner, right? A second electron, so it can compensate the rotational energy that it has associated with it. Okay, so here is, since the tertiary radical is more stable than the secondary, primary, methyl, that also tells you about the trend, right? The bond dissociation energy, BDE, bond dissociation energy. It tells you like which bond is easier to break. Here is telling you that here you can see the values of the energy. It costs you less to break a tertiary CH Why? Because breaking it, you generate a tertiary radical. Tertiary radicals are somewhat stable. So that's why here this CH is easier to break this CH. Why? Because if you break this CH right here, you generate a secondary, right? A secondary radical. If you break this CH right here, you are forming a primary radical. So these BDEs, right, bond dissociation energies, they really reflect which hydrogen is easier to break. So you have a compound like this. Let's say that I have this compound. Which carbon will be the one that is being attacked? I would say like this one is the carbon that's going to be attacked. Why? Because it's a tertiary carbon. As a tertiary carbon, it has a CH. That CH is going to be highly reactive. Why? Because if you break it, it will generate a stable radical. Is it going to be this one? No, it will be the second one, right? Why? Because that one will give you a secondary radical. This one will be the worst because this one will give you a primary radical. Okay? So it's always think of what if I create a radical? Is the new radical going to be stable? Not as stable, highly unstable, right? So you always have to evaluate depending on the branching because the radical stability depends on the branching, same as the carbocation. However, there is something that has been chasing us since chapter number 2 of this class, which is resonance. Resonance, it will be everywhere with you guys, even in organic chemistry too. It will chase you everywhere, right? So as we know, the resonance is really delocalization of electrons. And that also applies to radicals, okay? So even though radical, it is an unpaired electron, has no charge, but it has electron deficiency. That electron deficiency will create this driving force for the resonance to occur. And also, but it still follows the same rules. It has to be conjugated, meaning that radical, single, double bond. Right? So that's what we have to look for if you guys want to do resonance. This is what they call it allelic position. I'm gonna pause right now so you guys I can explain you now what is an allelic position. Okay, so far we have, let's say, this compound, right? This compound. This one, which one will be the atom, right? That will surrender easier a hydrogen, right? Hydrogen are going to be our targets in our reactions. Why the target the reaction? Because it's the bond that is easier to break. If you compare a CC versus a CH, CH is easier to break than a CC. CC costs you more energy. So if a radical has to attack this molecule, of course, it's going to attack it in the weakest point. What is the weakest point? A CH. CH is weaker than CC. It's never going to break a CC. It's going to break a CH. Now, among the CHs, there is also CHs tertiary, CHs secondary, CHs primary, and even CHs methyl. Why not? Yes, you can also have CH methyl. And of course, the radicals, even though they have no brains, but they know about the energy. So they know that if they break a CH, it will cost them less energy. Why? Because they will be producing a more stable radical, right? So in this case, I have this H, I have this H, and I have this H. Of course, I have more H's in the molecule, right? But I have these H's in blue, in purple, and in black. So which of the H's will be most able to remove? Let me see. 3 seconds. You tell me the answer. Blue, purple, or black? 1, 2, 3. Yes, correct. The black hydrogen will be the most stable. Why? Because if I remove the black hydrogen, I will be creating this radical. And that radical is a tertiary radical, more stable than if I remove the purple. If I remove the purple, I'll be generating a secondary radical. And then if I remove the blue one, I will be forming a primary radical. So definitely this one will be my most stable product. Now, what to do if you guys have, you want to stabilize your radical? So then you guys have to look for resonance. If there is resonance, I mean, it's not always going to be the case. So here I have a double bond and the same thing. The radical that is going to be attacking this compound, we have to look for the easiest bond to break. Okay. So by the way, when I say the radical, say like, Professor, what do you say that the radical is going to attack it? So the radical starts the reaction. Yes. Radicals are like zombies. right? I don't know if you guys have seen those movies about zombies, like a Friday 13, Elm Street, all those. I mean, I know they're from the 80s and 90s, but they're very old movies, but those are about really that a zombie touches you and now you're infected and now you have to infect somebody else. And then, right, so that one becomes a zombie, and then a zombie is a chain of zombies. That also same thing with radicals. Basically, the radicals, what they do is this. So let's say this one is a radical, okay? And these are normal compounds. This radical touches this molecule. Now this one becomes stable. Now this one becomes a radical. Now this one that is a radical will couple with this other one. This one becomes stable. Now this one becomes a radical. So it is a chain of reactions that always occur with radicals. And it's always like one radical always looks for stability. How can it look for stability? By attacking a regular molecule. A regular molecule now, this one that used to be reactive becomes stable. This one that used to be stable now becomes a radical. So this one has to attack another one so it can get stable. Okay? So then in that going back and forth, that's when you start growing a molecule. For example, this one binds to this. Now this side is radical. This one binds to this. Now this side is radical. Now this one binds to this. Now this side is radical, right? So that's how you start building a molecule, really, is by attaching one molecule to the other. As we will see the last part, which is called polymerization. Okay, so that's what we mean by radical reactions. It's always one radical attacking a normal, let's call it a neutral molecule. Now this neutral molecule now will become reactive. That's what you wanted. You wanted this one to be reactive. So you always you need to have somebody that initiates the reactivity. So that's why you start something, you have to use your regular molecule, which is this, and then you have to start it. Basically, you have to pinch that molecule. Say like, I want you to react, like, when you do a bad thing, like, oh, I want you to, right, behave or, do something. That's exactly what a radical does. Like, and then it touches, it pinches it, and then this molecule starts to react. And then that's how the reactivity of radical starts, okay? I know I'm using my hands to explain it, really. It's the best way how to kind of represent how radical reactivity is, but hopefully, I mean, you guys get the message. That is the idea, is like one really activates by a radical reaction. Now that this one gets a radical, now this one becomes very reactive. That's what we're doing here. So whenever a radical, which is the initiator, right? Let's say like radical X, right? A radical X will attack this molecule. Of course, it has to attack the weakest bond that is in this molecule. So here you will say, like, okay, Professor, I see here that you have a primary carbon, secondary carbon, secondary carbon, secondary carbon, secondary carbon, primary carbon, right? Primary, secondary. So technically, I should do it in the secondary carbons, not the primary, right? Because the primary, I know that it's the least stable. So, but now, is there any difference between this with these secondary carbons? Yes, that this, guys, if you remove it here, this one will be conjugated. You see it? It's like that. Yes. You form the radical there. Your radical is conjugated. You see? Radical, single, double. So it is conjugated. What about this side? Is this also conjugated? Yes. If you do it in the other side, that's also conjugated. This is what we call the allylic position. It's the position that is conjugated to a double bond. Okay? And it's not only applying to radicals, it really applies to any molecule. So for example, if you tell me, oh, okay, so I have this compound, what are the allylic position of this compound? Okay, so I will tell you the conjugated carbons that are to this is this one. That is conjugated, you see? This one is atom, single, double. That's allylic. This one is also allylic because it is atom, single, double bond. Okay? It doesn't have to be like a long conjugation. I mean, if it's a long conjugation, that works too. I would say like, is this an allylic position? Yes, this is an allylic position. Why? Because it's conjugated. Atom, single, double, right? So it is conjugated. Now you would tell me, okay, is this one also conjugated? Is this also an allylic position? Technically, yes, it is an allylic position because it is conjugated like atom, single, double bond. But for radical reactions, it's useless. Why? Because we say that always you want to break CHs. And this particular carbon does not have CHs. It's all C, 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 carbon, 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 all carbon, carbon. This one has Hs. So the radical reactivity is way higher here because the CHs are the weakest bonds that you can break. Okay, so going back to this position, so that is what we want to this compound. This is what we are looking for, the allylic position. Those are the most stable. Why? Because the radical that you're forming is not only secondary, it's secondary plus resonance because they undergo resonance. I will do with a very simple resonance. Let's say this one is my allylic radical. If you want to do resonance, right? So you do a fish hook. The radical will move towards to form a double bond. See, this double bond gets broken homolytically. Gets broken. This one gets broken. So this double bond, sorry, this radical induces the homolytic cleavage of that double bond. That pi bond breaks apart into two. So it will break it, and it will cause that these two now are forming a pi bond here. What happened with this other one? This other electron that was part of the pi bond now is sitting on that carbon. Okay, so basically induces, right? It's like the bad friend, right? The bad friend that sees a couple of friends that are very get along well, and it breaks it. So break the friendship of these two, breaks the bond, and then it forms a new friendship with a new chemical bond. And now this one is alone. But this process goes back and forth, as we know, resonance, right? So they're both is bouncing between the two. But that's how you represent a resonance. Another example for resonance for radicals, let me see. This one is important. This one is actually longer. Radical, right? If you want to represent the radical resonance here, this one is the one that's conjugated, right? You see this pi bond, right? So this one will ask, it's conjugated, it will form a pi. This pi, right, breaks. One goes with the other, right, with the original radical, and this one will go to the carbon radical. Now this is a double bond, and this one now becomes a plus. Sorry, not a plus, a radical. Okay. You see, so this pi bond, right, breaks into two. One goes with the initial original radical, forming a double bond, and this one, the second one that got broken, goes to the sits on the carbon as a radical. No charges. The only driving force is the ampere electron. Now, if you guys want to continue with the next resonance structure, now this radical induces the homolytic cleavage of this pi bond that is conjugated, radical single double. It induces it, it will go here, and this one breaks apart into two. Again, these two electrons, right? This one goes to the, always fish hook. Always see my arrows is fish hook. So now what you're forming is a new pi bond right here. And now this one gains the radical. I keep going. This one goes, breaks, right? This pi bond breaks, and this one goes to the carbon. Double, right? Another radical. And that's it, right? So that is because if I return it, I mean, if I do one more, I will end up going back to the starting material, right? To my original sample, because I'm breaking, it's a ring, right? In a ring, you always have to go back to the starting point. So these will be the 4 resonance structures for this radical. This one is called a benzylic radical. Very famous, very popular. I don't know, I think I do. I just had it here. Let me see. Okay. kind of shiny. You cannot see it really. Maybe you guys can read it here, what it says. I mean, you guys read it? No? Yes, no, you guys can read it. Let me see, I'm gonna focus the camera so you can, yes, you can read it. Yeah, what do you guys read here? Benzoate, right? Preserves freshness. What is this? It's it preserves the food. It's anti-fouling. It's an anti-fouling compound. Why? Because benzoate looks like this. These aromatic compounds are excellent, excellent radical stabilizers. Why? Why is it an excellent radical stabilizer? Because you can see that the aromatic rings, they kind of entertain the radical. See, the radical is supposed to be reactive, but the radical also stabilizes itself by going around the ring, around the ring, around the ring, around the ring. So basically you lose the reactivity of the radical when you guys have aromatic rings or these benzene rings. So benzoate, for example, that's why they put it in every single food that you will find, you will find the benzoate. Okay, so that potassium benzoate, I mean, the potassium doesn't do anything. It's really the potassium. So if there is any fouling that happens in your food, normally happens through radical reactions, right? The decomposition as a product of the oxygen. The oxygen is really the worst radical producer. The worst in the sense like it produces a lot. It's bad for our bodies, for life, because it produces a lot of radicals. That's why you're aging. Right now, for example, I'm breathing, I'm aging. Okay? So every time that you are breathing, oxygen goes into your body, that oxygen ages your body. Okay, so now should I stop breathing? No, because unfortunately the oxygen is also associated with respiration in your body. ATP, which is the molecule of energy in your body, requires the uptake of oxygen. So at the same time that you produce energy, you're also aging. Okay? So aging is associated with oxygen uptake and part of your metabolism. Okay? So this radical stabilizer really it deals with anything that has oxygen, right? I guess things get oxidized with oxygen, so it produces radicals. So this particular compound, which is called benzoate, it has an aromatic ring or a benzene ring. That's why we call it aromatic or benzene ring. Okay? So this one, if something happens inside your food, this guy will go first. Say like, is there any radical? Yes. Okay. It traps it, and then the radical gets trapped in that ring. Right? So that's really what this molecule is going to do as a radical stabilizer. Right? So we did the resonance. Okay? So that's a good thing that, hopefully, there are no questions about the resonance. Let's continue with the slides. Here is the example I was telling you. Benzylic radicals, right, are very important, right, because are more stable than allylic radicals. Allylic is this one that I showed you before. Allylic is this one, this short one, because it's only one position conjugated. But if you have a series, right, sequential double bonds, that makes it more stable. One of them is benzylic. Benzylic is part of a benzene ring. It's more stable because the radical is delocalized even more carbon atoms. What if, Professor, what if I have two rings? Let's say like you have this compound and you have this one. Is this going to be more stable? This one that has two fused rings. Yes, definitely. That's going to be way more stable. Then why don't they use it if it's more stabilizing? Because remember that molecules, they have different solubility issues, right? When they are bigger. So if benzoate, well, this is benzylic, but if one ring is already hard to dissolve in water, you can imagine two rings. Two rings is even more, right? It's more difficult. If I put three rings, it would even be worse. Okay, so of course you gain radical stability, but you also lose solubility and other physical properties. Maybe this compound can be liquid, but this one is definitely not going to be a liquid. It's going to be a solid. So you want some properties also for your ingredients or whatever substance you're using. to be the most friendly to your process, right? In this case, the food process, right? Or maybe in the physiological process or in the respiratory process, right? So things like that, you really have to be careful and then see, I want stability or I want better physical properties. In this case, they prefer both stability and physical properties, and apparently benzylic radicals are enough, right? So this one is the very similar system that I did. I only did 4 resonance structures. They came up with 5. Well, but it's because the first and the fifth are the same, right? So there is no difference. So they also came up with 4 resonance structures. Okay, here's also something very important that is not as usual as carbocations. Remember the carbocations, we said that tertiary carbocations are always more stable than secondary, secondary more stable than primary. Here for radicals is not the case. In radicals, resonance stabilized radicals are more stable than tertiary radicals. So you have a simple tertiary radical. That simple tertiary radical with no resonance will be less stable than an allylic radical. You said, oh, but professor, this one is a primary radical. How come? This is not a primary radical. This is an allylic radical. That's different. It looks primary. Yes, you guys are right. But it is allylic because that primary carbon is conjugated to a double bond. So it's not a primary radical. It's an allylic radical. And this guy is a benzylic radical. It looks primary. Yes, I agree with you 100%. But it is not primary. It is benzylic because it is conjugated to a benzene ring, which is right here. Okay, so I want to be clear that this particular, oh, but I have another example, right? You know, you guys know, I like to talk a lot and give you more examples, right? So tertiary, I'm going to focus it, just give me a second, yeah. Tertiary are less stable than allylic, less stable than benzylic, right? Radicals. But even in benzylic, you can have a difference. So for example, if you tell me, oh, professor, which one is more stable? This one, or this one, right? Which of these 3? You say like, oh, they are all benzylic. Yes, you guys are right. They're all benzylic. But this one is a benzylic that is secondary. This one is a primary benzylic. And this one is a tertiary benzylic. Which one is more stable? Of course, this one. They're all benzylic. But remember, they're all benzylic. What about this one? This one will be a tertiary radical. So which one is the most stable? Still this one. Because this one is tertiary. Well, this one is benzylic and also tertiary. This one is benzylic and secondary. This is benzylic and primary. And this is tertiary only. This one is the least stable because it's only tertiary. They're all benzylic. Benzylic definitely boosts the stability. This one's an S. Okay. Boost the energy by a lot, right? So the benzylic, they're always going to be more stable than the non-resonance. So, but among the 3 benzylic, of course, the more branches will be more stable than this one secondary and this one primary, right? So just keep that in mind, that always you can combine the effects, right? Of only branching or only resonance effect, right? So let's continue with the next slide. So here, something that you guys are gonna like, and I also like when I was a student, is that radicals never do rearrangement. Do not undergo rearrangement. Okay, so in the mechanisms of the radicals, yeah, you will always have patterns. You like remember in our reactions on chapter 6, we were talking about proton transfer, nucleophilic attack, CCR, and loss of leaving group, right? Here in radical reactions, we will have different patterns. Now, do we need to know all of them by name? No, you don't need to know. You guys don't need to know by name. You only need to know the 4 mechanisms, the 4 reactions that we learned that I highlighted at the very beginning in the outline. And even 3 of them, no, 2 of them, they are identical, are very similar. It's really 3 reactions that we need to learn in these 3 mechanisms that we need to learn for this chapter 10. Okay, so, but radical mechanisms are distinctively different. Yeah, they are very different because first you're using fish hooks. Second is that you need an initiator, right? Remember at the beginning, I was telling you, you need an initiator that is going to attack a neutral molecule to make it reactive. That makes a difference. You didn't need to do that in SN2, for example, or in E2 reaction. You didn't need to activate something, right? The molecule just had a leaving group and then it was attacked by the base or was attacked by a nucleophile. It's not an activation, it's a reaction. Okay, so here, this particular compound, it will rearrange, the carbocation rearranges, but the radical does not rearrange. Okay, so there are 6 patterns in radical mechanisms. We don't need to know all of them, but if you get familiar with them, that would be great. Homolytic cleavage is the first one, right? You see the fish hook, it breaks up into two radicals. Addition to a pi bond, you see that radical attacks a pi bond. Hydrogen abstraction, remember, be careful that this is not a proton transfer, but the radical abstracts the hydrogen. Halogen abstraction, now a radical abstracts the halogen, right? You can see that, what do they all have in common? Like you see this one, what I was telling you, an initiator. This one is your initiator, initiator, initiator here. There is always a molecule that initiates the reaction. A radical reaction always has to be, it needs that spark to run. If it doesn't have that spark to run, then you cannot do a radical reaction. Who is going to do that spark? These guys. Heat or light. This is the one, right? The homolytic cleavage is the initiation, right? Initiated by light or heat. That's really the initiation step. This initiation step will always happen in every single reaction. Why? Because that's the one that produces the radicals from a neutral compound. Here, neutral compound to radicals, but here, no, one radical, one neutral, one radical, one neutral, one radical, one neutral. No, they are all similar. The only one that is special is this one right here. There's one more elimination. Here I can see a radical that produces a neutral, and then decoupling. That's a closing step. Because if the reaction is initiated, that means that the reaction also has to be terminated. So this one is what we will call a termination step. Right? Because everything that starts should terminate, should end. So this one is going to be a termination step. Why? Because it converts two radicals into a neutral compound. Right? Okay, so let's see. Patterns in radical mechanisms, it can be divided into 3 steps, 3 large steps, right? The steps in a radical reaction can be called initiation, termination, and propagation. Okay, so those are the steps, and that's not the order. I think they made a mistake with the order. It should be initiation, propagation, and termination. What happens in initiation? Initiation is the step in which the radical species are created from a non-radical species or non-radical molecule. For example, here I have halogen. I apply light and heat, and I break it into 2 radicals. 2 radicals you have right here, right? So this one can be bromine, can be chlorine, right? We will see that fluorine and iodine are not that reactive. Well, fluorine is too reactive, and iodine is too slow. So here, bromine and chlorine will be the ones that we'll be using. So you have Br2, Cl2. They break into 2. They split, homolytically split, and then you get 2 radicals. Those 2 radicals, they will do chemical reactions. Reaction this way, reaction this way. They will take their own paths, okay? So the propagation is the next is the propagation is when the radical that you created in the initiation now it starts to infect, let's call it like that, infects a neutral molecule, right? So as I was telling you before with my hands, like one is a radical, is shaky, it will activate the second molecule. The one that I really want to activate will be activated by this radical, and you start to make the product. The product has to be made in the propagation. Okay, and then of course the propagation can be any of these steps: addition to pi bond, hydrogen abstraction, halogen abstraction, or elimination. Any of those 4 steps will be inside of your propagation step. Now, do I need to memorize all of them? Do I have to recognize them? Do I have to label them? No, you don't need to label them. It will come natural when I do the sample mechanism for halogenation of alkanes. Okay, so don't panic right now. You don't need to know. You know, I know, professor, by now I'm tired of chapter 8, chapter 9. I had about 20 reactions to memorize to now I don't want more memorization. Yes, I agree. So you don't need to memorize these reactions. You only need to apply them. Okay, so no naming, no recognition, only use it. So that's the best way how to study radicals. And then to be honest, radicals, even though it's taught in organic chemistry 1, but it's the only type of reaction. There is no chapter radicals 1, 2, 3, 4. No, this is the only time that you will see radicals. In organic 2, you will not see radicals at all, unless it's a review. There is a chapter called I think it's chapter 12, about synthesis. Maybe that one you will see something about radicals, but new things on radicals, nothing. Everything of radicals will be here in chapter 10. And the last step in a mechanism is determination. Is when two radical species, they cancel out. Basically, they cancel out two here, right? You have this one and this one. They react, they get together, and they form a neutral compound. Okay? So this determination, do I have to terminate radicals? Yes, because whatever started as radicals has to end or consume those radicals. Okay, so the complete definitions, right, will be discussed later as we do the mechanism. This one is one of them, chlorination of methane initiation. I will tell you how it works. Nothing better than doing it by hand. You know me by now, so you know that it's the time for me now to open my camera. All right, so we are going to do halogenation of alkanes. That's the first reaction. Now is the time that you guys can take notes. Whenever you write a halogenation of alkanes, a mechanism, you always have to start with a subtitle, initiation. Initiation, okay? What is going to happen in initiation? Oh, here the reaction. The reaction is going to be, let's say, propane plus chlorine with light produce 2-chloropropane and HCl. Okay. This is the reaction. You have to write the mechanism of it. Like alkane, halogen, light or heat. It will create a chloropropane, 2-chloropropane, and HCl. That is extra, right? I mean, you don't have to really. This one is the one that you guys have to be concerned about, right? How to produce this one. Okay, initiation. Which of the two is going to be an initiator in this particular reaction? Chlorine. Chlorine is my initiator. How do you know that? Well, because chlorine, they have a high affinity. I mean, not high affinity, but they react easily with light and heat. Because of all the polarizability of the compound. But they are not using the polarizability. Okay, first reaction is the initiation. What happened with this halogen is that this one will, induced by the light, it will break apart into two. I know that fish hook is horrible. Well, they look like fish hooks, but let me show you erase it. Do a better fish hook. Sorry about that. Oh, the same. Okay, that's a better fish hook. This one, no, that's too open. Okay, let's say like that. Two fish hooks. I mean, if your fish hook is not perfect, that's fine. I mean, it's not a big deal out of that. Okay, so the chlorine splits by the action of the light into two chlorine radicals. That's it. That's the main goal of your initiation, is that you produce a radical, right, from a neutral compound, and that radical is involved in your product. If you produce a radical that is not involved in your product, then don't even bother. You have to continue one more step. But in my case, chlorine radical is in my molecule. Not as a radical, but I see chlorine in my product. So I can stop the initiation. What if you produce something else, say OH radical? Should I continue? Yes, you should continue. Why? Because the OH radical, I don't see it here. I don't see OH. So maybe make OH react with something else so you can create either the Cl or the alkyl radical. In this case, I created the Cl and the Cl is in my final product. So then is propagation. Now, Professor, all the halogenation reactions have the same steps? Yes. So you have to learn it only once and you just change it to whatever is the halogen or is the substrate. In this case, this is my substrate. Okay, next is the propagation. I bring the chlorine radical that I created, and I will make it react with my substrate. This one is my substrate. Now, which bond is gonna be attacked or broken by the chlorine radical? We said that the chlorine radical will always look for the weakest bond to break, right? In this case, this one is a primary CH, secondary CH, primary CH. Of course, it's gonna break the secondary CH. Why? Because that's the most stable. It will create the most stable radical. Now, can it also break the primary CH? Yes, it can also break the primary CH. We will see that chlorine has no selectivity. That's coming later. But for now, I'm just going to tell you that, yes, chlorine cannot distinguish that easily between primary and secondary. That's another issue. It's really not related to the stability of radicals. It's really a chlorine issue, but that's coming soon. Okay. So, but for now, let's just follow the stability. And we know that according to stability, the secondary CH is the most, right? It's the easiest to break. And also in the product, I see that that one is the one that is reacting. Here, I see that that one is the one that reacts. So it makes sense for me to break that. So I'm gonna do a fish hook here. What is this halogen going to do? This halogen is going to break this bond. See this bond between the CH? So it will, as the chlorine will steal the hydrogen will come, and then this one will go back to the oxygen. Sorry, to the carbon. So here you form HCl plus radical. See, the chlorine radical breaks the CH. The CH breaks into two, right? Homolytic cleavage. The H radical goes with the HCl, clicks. That's a hydrogen abstraction. I mean, don't worry about the names. I'm just need the hydrogen abstraction, and you form a radical here. See, this radical infects this molecule. Now this one becomes a radical. See, that's exactly what I was telling you about the zombies. Now, did I create my product? Yes, I created one of my products. HCl, I created, done. That one is done. Now I have to make this one. How can I make that one? Okay, so propagation, you guys have that one that you produce, and then you will make it react. Now you will say like, oh, professor, can I make it react with the other Cl radical that you created? No. Why? Because in propagation, you only make react neutral compounds with radical. Radical with neutral. Radical with neutral. Neutral with radical. You cannot make react in propagation two radicals. Two radicals never react in propagation. So you make react two radicals in termination, not in propagation. Propagation is neutral with radical, radical with neutral. Anyway, like any manner that you want, but always have to be different. Same thing here. Here in initiation, you're supposed to split. That's what I did. I cannot have here a radical plus a neutral, unless I have to do a second step of initiation. But normally it produces only one only one reaction. You will see that for the HBr reaction, you need a second step. That is an exception, but normally for halogenation of alkanes, you only have one step, initiation step. Okay, so in propagation, I cannot bring the Cl radical. It would be ideal because that will give me the product, but I will have to bring the ClCl. This one here, this bond, it will be broken homolytically by this radical. These two will get together and this one leaves. So now I get this compound, which is the product, plus Cl radical. See, that's a good propagation step. That you break a neutral with a radical. And then I created my two products. My two products are right here, right? HCl is one product and the 2-chloropropane is the other. Now you say, like, professor, what happened with this Cl radical, right? This Cl radical goes back to the starting point and is a chain of reactions. It's a chain reaction. This C radical will go back to the starting point, consume another propane, produce these products, and then creates another Cl. That new Cl radical will go back to the chain. See, it's a chain reaction. When is this gonna end? This ends until you run out of propane. Once this one is done, then the chain of reaction will stop, of course, right? Because this one is like a circular motion, circular reaction, because this one Cl goes back to its first point of the propagation and does the reaction again over and over. You will be producing more HCl, HCl will go up in concentration. This one, the 2-chloropropane will also go up in concentration, everything until you run out of this or this one, right? One of the two. Eventually you will run out of any of these two reagents, right? That's propagation. And last is termination. In termination, what you guys have to do is you just have to cancel out all the radicals that you have. Okay, so what radicals do we have? Okay, so I'm gonna circulate with a pencil. Radicals that I have this guy, I have this guy. That's it. So I'm going to match them. So what do you mean by matching them? So Cl, right? Cl radical plus another Cl radical. Cl radical plus this radical. And this radical plus itself. Okay, you see? All these are my only radicals, right, that I have in my entire reaction, in my propagation. So this one, this, no radical, another radical, another radical, this one. These are only my only 4 radicals, but really 2. So I will just match them. I will do self-termination and cross-termination, right? So Cl radical plus Cl radical, they self-terminate, giving you Cl. This one self-terminate, giving you actually the product. And this ones will also self-terminate to give you this compound. Okay. Those are my termination products. Do I have to show them? Yes. These are not my real products. Yeah, I know. But you guys have to show them in the termination step of a radical reaction. Always, always, no matter what. I learned it. My teachers learned it. You always have to do the termination step in any termination, in any radical reaction, right? So definitely we'll do more mechanisms like this. I can do one more. I mean, I don't want to make the lecture so long. Maybe I will put one more of these mechanisms in the solve problem video so you guys can get more practice on this. We'll have more mechanisms anyway to do. Okay, so let's go back to the slides. On the slides, we have the methane. Here they started with methane, chlorination, chlorinated methane to form methyl chloride and hydrochloric acid. The first step is very similar to what we did, right? It's a homolytic cleavage. It's a homolytic cleavage of the chloro bimolecular chloro. The chloro molecule with light gets split into 2 radicals. You can see here the 2 radicals. Okay. Next is that in the propagation step, now this radical, this one should be an H. There's a typo here. Should be an H there. This radical now attacks the hydrogen, the weakest hydrogen. Remember, the weakest hydrogen, the weakest CH bond attacks, abstracts. It's a hydrogen abstraction. You don't have to be worried about this name. I mean, if you remember it, great. And then you create HCl, which is one of your products, and a radical. Here it should be H. Okay. That radical now attacks a chlorine molecule with a halogen abstraction. And you generate your second product, and you also form that radical. This radical goes back to the starting point and continues the chain reaction, right? Remember that radical reactions are chain reaction. And termination, when you do in termination, as we did it, we match all the, right, all your radicals self-terminate, right? Self-terminate or cross-terminate here. Self-terminate in this case. Okay, so those will be your termination product, right? So termination with radicals collide and couple. That is as now, one problem of the radical reaction is that there is very difficult to control. Control in the sense that the same way as 1 chlorine can be added, a second chlorine can be added, a third chlorine, and even a 4th chlorine. Okay, so polychlorination is difficult to prevent. Why? Because the chlorinated product is more reactive towards halogenation than the original material. Okay, so for example, this methyl chloride is more reactive. It will go to the second chlorination third chlorination, and fourth chlorination until you get all the way to carbon tetrachloride. So the only way how to control it is by time and also regulating the ratios, right, between methane and chlorine. If you have too much chlorine, of course, excess chlorine will give you like a tetrachlorination. But if you have limited reagent as chlorine, yeah, definitely you can control that, the production, right, of the polychlorinated products, right? So for example, methylene chloride, which we have been using in the lab a lot, chloroform as another solvent, and carbon tetrachloride, which is very toxic. I mean, these are all these chlorinated or halogenated solvents, they're very toxic, so stay away from them. Initiators, right? So the initiators that we've been, that's something always also very important to discuss, is that initiator that we've been using. For example, in the previous reaction, halogenation of alkane, we use halogen, right? Halogen here, dihalides. This is the dihalide, the one that we just used. Chlorine can be bromine. It breaks into two in a homolytic cleavage, and you get two chlorine radicals. Alkyl peroxides are one of them, and acyl peroxides is also one more. Now you can see here what happens. Where have you guys seen this molecule? In HBr peroxide, right? Remember HBr peroxide? That one. That is giving you a hint that the reaction follows a radical reaction, the HBr anti-Markovnikov addition to alkenes. Okay. So now, out of the three, which one is the most reactive? Of course, this one, because it needs less energy to occur. Acyl peroxides are the most reactive initiators that you have. Most likely, I would predict that in the industry, they use acyl peroxides. They don't use alkyl or dihalides, alkyl peroxide or dihalides. Why? Because they take too much energy. You need to apply too much light or heat to make them react, to produce halogens. So the easier to produce halogens are acyl peroxide. Acyl peroxide will produce radicals pretty instantly. Okay? So the acyl peroxide is most reactive and it's effective at 80 Celsius degrees. So you don't really need to apply too much heat for them to react. Inhibitors, the same way as you can have initiators, inhibitors is like they react with radicals and prevent the chain process from initiating or propagating. One of them is oxygen. Oxygen, it reacts with they oxidize the radical. So basically they prevent the chain reaction. Why? Because oxygen is also radical. Okay? So you can see oxygen. Oxygen is a diradical, so it traps. So if you guys have a radical, let's say you have the chlorine radical here, this radical will definitely trap it. And you have another chlorine radical, it will trap it. So oxygen kills any type of radical reaction. Why? Because oxygen itself is a diradical. So it will react with the radicals that are in your reaction. And oxygen is a gas. If it's a gas, it can go everywhere at once. It's not like a solid or like a liquid. Oxygen will go everywhere. So that's bad. For most of the radical reactions are very slow in presence of oxygen. Why? Because oxygen traps them. Another one that is used is hydroquinone. Hydroquinone is this molecule. You can see one of the reasons. I mean, let me see, give it a thought. What do you think that hydroquinone traps radicals? Let's see, 4 seconds for that. Correct. Yes, it's because of the benzene ring. The benzene ring by resonance traps radicals. So if this radical, if a radical touches hydroquinone, definitely that radical will be trapped inside, right? With this resonance stabilization with the pi bonds, right? So there's a lot of stabilization, then the radical reaction is inhibited. There is no reaction. Why? Because the hydroquinone prevented, right? The chain reaction. And any benzene ring really, I mean, that has this one has the OHs that makes them more reactive because oxygen are also very reactive towards radical reactions. But the main reason is because of the benzene ring. The benzene ring will create benzylic radicals and they are highly stabilized. Okay, now let's see the details of the halogenation thermodynamics. These reactions don't work well. The only halogenations that are useful are chlorination and bromination. Iodination is endothermic. It needs too much energy. So that's why it is not thermodynamically favored. It's too much energy. Maybe breaking up homolytically, the bromine maybe takes too much energy. In fluorine is so exothermic that it's not practical. So basically it burns everything. So at the same time that it's created, maybe this guy reacts with this fluorine, right? Excess fluorine or something. Or maybe the HF adds too quickly that you get CF4, let's say, right? So the fluorination is so exothermic that it's not practical. It's too violent. So it releases too much energy that maybe give you a lot of side products. And the iodination is too slow. Why? Because maybe the iodine doesn't break that easily. It takes too much energy, right? You can see here the amount of the delta H, the enthalpy, it is plus 55 kilojoules per mole. And fluorination is too much energy, minus 431. Wow, there's a lot of energy that is released by just 1 mole of the chemicals. Okay, so for halogenation, only chlorine and bromine are the ones that are used. Now let's see which one is better, right? So now between chlorination and bromination, which one is the most efficient, or is there any difference because of size, because of energetic reasons? Here's an example. The first step of the propagation, first and second steps of the propagation, see how much energy it costs. For example, the first step is the hydrogen abstraction, right? In chlorination, it costs minus 21, exothermic, right? For bromination, this one is endothermic. Look, the first step is endothermic. For the second step, they're both exothermic, right? 96 and 92. That's a difference. Why? Because this one is the not limiting rates, right? It's not the slowest step. The slowest step apparently is this one. The first step is the slowest step because it takes you more, right? It releases less energy. And in the case of the bromine, is the most endothermic. So that will make a difference. Why? Because if the process of the radical formation is slow, that means that bromine will be able to distinguish better between the radicals it's forming. So if a reaction is too easy, the molecule, the reactants, they will just react without distinguishing, right? Why? Because it doesn't cost you that much energy. Let's say like, oh, bananas cost me like really $1 each. Okay, I don't care if the banana comes from Mexico, from the Caribbean, if it comes from Colombia, if it comes from Brazil. I don't care because it's so cheap, right? It doesn't cost me that much. But what about, let's say another fruit that is, let's say mango, right? Let's say mango. Mango is more expensive. So if I'm gonna pay money for an expensive fruit, I want the best fruit, right? Don't you think the same way? So if I'm gonna pay energy, right? If it's gonna cost me 42 kilojoules, like you see here, if I have to pay 42, I want the best, the most stable, right? The most yellow mango that I can see, or the most red mango that I can see, right? Depending on what type of mango you guys prefer. But I want the best. That's exactly what bromine has. That it costs so much the first step that bromine will be more selective. If I'm going to spend money, if I'm going to spend 42 kilojoules, I want the best radical that you can produce. Why? Because if you don't give me the best radical, it will cost me more. Why? Why? Because tertiary is more stable than secondary radical, more stable than primary radical. In the case of chlorine, no. Chlorine, they're all so low in energy that chlorine doesn't really care. Oh, forming a primary radical costs me about the same as forming a secondary radical, or costs me the same as forming a tertiary radical. So I don't really care if I form a primary, secondary, tertiary. That's what chlorine thinks. And you can see it in this particular diagram. This one is chlorination and this one is bromination. Chlorination, see, the first step is really like a low hill. For the bromination, is a really steep hill. So that high hill, that high activation energy really makes the bromination more selective, okay? So what is the consequence of this? So here is that the halogenation, right? Two monohalogenations are possible for propane, right? So in this case, let's imagine propane. Propane, you guys will have two primaries, right? Two primary carbons and one secondary carbon. So Statistically speaking, you have 6 options for primary radical formation and only 2 options for secondary formation. So chlorine is indiscriminate, meaning that it doesn't care. So it will produce secondary radicals or primary radicals, right? So primary radical that will take you to that product. So it doesn't really care. Why? Because the first step of chlorine is so easy, doesn't need that much energy, that it will produce both of them about the same amount. So that's why you see 60% and 40%. Okay? But for bromine, that's not the case. Bromine is much slower. So since it costs more energy to bromine to form the radical, of course, it wants to form the most stable radical, so it costs less, right? So it's more selective. So in this case, the secondary bromine is going to be the major product. You can see here about 97%. So bromine is really sweating this reaction. That's why it wants the best. The primary bromination is only about 3%. Okay, so in this case, bromination is more radioselective. What is the bottom line of this, right? Why am I explaining all this to you? Because if you guys are going to use this for synthesis, bromination is the way to go. Okay? So always bromination, always think of bromination, 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 bromination. Why? Because it's the most radioselective and it will give you the major product as the most stable. Now, can I use for synthetic application the chlorination? No, because you get about 50-50, 60-40 is too much, right? There is really no major product. I mean, there is major product. You could say like, yeah, oh, Professor Navarro, 60% is major product. Yeah, I know. But what is a better major product? This or this? Of course, the 97% is a better major product, right? So anytime that you guys are doing synthesis, please go with bromine. Bromine is the one that really decides. So here, this one is a condensation, right? Or like a summary of the difference between the radioselectivity in bromination and chlorination. Here is chlorination and bromination. Chlorination 65-35%. That one is with tertiary. That is a tertiary position. Bromine is about 100% versus primary 0%, nothing of the primary. Whereas in the case of chlorine, you get 65 for the tertiary and 35 for the primary. You could even think that chlorine, come on, you have to give me the most stable radical, but no, chlorine doesn't care. Chlorine will definitely give you more, like a more even, right? Even, I mean, definitely there is some, right, preference towards the tertiary radical, but by looking at that 65-35, I would really be discouraged. So I want a cleaner reaction, and the cleaner reaction is only given by bromine, right? Bromine will give me a tertiary, right? It follows better the stability trend, right, that we know for radicals. Here is they study for most of the halogens. They didn't do for iodine because we said that iodine is very slow anyway. Here is fluorination in fastest process, right? So it's not selective at all. So fluorination, 1 primary, 1%, no, not 1%. Selectivity rates, right? Or proportions, right? 1 primary is about the same, see? For bromination, 16,000 preference over 82 over primary 1, right? So you can see that definitely there is no chance that in bromination you can get primary in presence of secondary or secondary in the presence of tertiary. But for chlorine, it's a more even competition. 1, 4.5, 5.1, 1.4, 1.2, 1 for fluorine. So which one is the most selective? Radioselective, bromination. So just go for bromination, bromo. Great. Now, is there any chirality in halogenation reactions? Yes, if you have a chiral center. Remember that radicals, right? If you have a radical, you guys have an sp2 carbon. The radical is, let's say, like the radical is right there. I have a p orbital. The p orbital can be attacked, right? Let's say like here I'm doing a C plus, a C radical. This one can attack here, or it can also attack at the bottom. Right? So you can have the attack on both sides. That creates that the radical can be attacked in both sides. If it's both sides, and if your radical is prochiral, of course it will give you a chiral center. You will have two you will get a racemic mixture. So you will get both. Racemic mixture, remember, means 50-50, right? So here the chlorination, I know that we know that it produces a primary also, right? Because chlorine cannot really distinguish. But here will be your secondary carbon and a primary carbon. So this one is chiral, you will get a racemic mixture 50-50. What about this one? Yeah, that one will be smaller, right? Smaller than that. Bromination, same. Here you don't get a primary or secondary. Why? Because bromination is more selective, right? Remember, bromine is more selective, so it will only, bromine will automatically scan the molecule. I will say like any tertiary, no, okay. Then go to the next one. Any secondary? No. Any primary? Yes, okay, 2 primary. But in this case, in this particular molecule, I find a tertiary, so bromine will target that tertiary and it will create the bromination product. And since that bromination creates a chiral center, that chiral center can be is chiral. It will be producing a racemic mixture, meaning that both products will be obtained only because it's chiral. Okay, so a racemic mixture will be obtained. The chiral center is a tertiary carbon. It has a weaker CH bond. Yeah, right. We went over already that. So the weaker, the radical will always target the weakest bond that is present in your substrate. Now what happens with allylic, and that is our second reaction, allylic halogenation. We said that if you find a double bond, right, you guys have conjugated position, which is called the allylic position. Now, at the allylic position, also following the same reactivity, the same, yes, but now you will be forming an allylic product, okay? So alkenes selectively undergo H abstraction and the allylic position, okay? So again, I have to do the allylic. In this case, allylic halogenation, but as we know, the most stable is the bromination. So I will do the allylic bromination. Because remember that the bromination is the most selective. So if I have this compound, yeah, let's do this one. Okay, so I will mix it with bromine in light or heat. Okay, I will get this compound plus HBr, of course. Why here? Because that's my weakest bond, right? Remember that the radical will always target the weakest bond that is present in my substrate. In this case, I have a primary CH, secondary CH, secondary CH, secondary CH. But this secondary CH is resonance stabilized because it will be radical single double. That is my most stable. What about this one? Professor, what about this one? This one is called a vinyl. I don't know, yeah, I mentioned that, a vinyl. Why is it called a vinyl? Is it the same as the vinyls that they used to play music before, right? With the music, yeah, they used to rotate and then they had the needle to play the music. Yes, it's the same vinyl. This is called a vinyl hydrogen. That is not as stable because it's sitting on an sp2 carbon. sp2 carbon, but once it loses, it would it be sp? No, it wouldn't get sp. It would be like a weird sp2 once it loses the hydrogen. See, the vinyl radicals are really not as they're definitely not stable. Okay? And then this one would be also vinyl hydrogen. Okay? They are not stable, vinyl radicals. Okay? Don't even think of the vinyl radicals. So the only option that I have is the hydrogen. So let's do the reaction. And that would also be used as a practice for mechanisms. Initiation. First of all, the initiation, I take my halogen, bromine, with light, right? I use light. What is the symbol? H nu. If you remember from Gen Chem 1, E is equal to H nu. E energy is equal to the Planck's constant and frequency. That's why we use this as, we call this light. Instead of writing light, we just use H nu. Okay? H nu, that's what it really means, light. So this one will create or will make the bromine to split homolytically. So I will get bromine radical plus bromine radical. I'm done, right? Why? Because the radical that I formed is part of my product. So I stop right there. Next is propagation. That radical that I just made, I will make it work with the or react with my substrate. I identify my weakest CH, and I'm showing it there. What happens here? Okay, here it's not going to attack the double bond. My weakest bond is the CH, so I will make it like this. This one. Okay. Kind of represent the homolytic cleavage. See, here I'm putting the arrow of the bromine, getting together with the H. I'll just make the two fish hooks to get close, right? So they don't have to overlap, they don't have to cross, but at least here I'm showing that these two fish hooks are getting closer, meaning that they are forming a chemical bond. And this other half goes to the atom. Okay. So what happens here is HBr, okay, because the H and the R, this one is a hydrogen abstraction, and the allylic, okay, the allylic radical. Now, this allylic radical can go through two paths. Okay? So that's an alternative because here it can get resonance stabilized. I'm going to do it here. Resonance stabilized between these two, right? It's resonance stabilized. So technically, I can get two products. One in the secondary and one in the primary. You will say, like, oh, but professor, the secondary allylic should be more stable than the primary allylic. True, very true. So I should get slightly more of this product than this product, but not for too much, because remember that allylic is already highly stable. So secondary and primary won't make that much difference. You will get slightly more of this though. Yeah, you guys are right. This one should give you more product than this one. Okay, so let's do it only the mechanism with this one. Okay, so next could be my allylic radical reacts with a second bromine. Why second bromine? Oh, because the first one was used here. Bromine, and then I will make the fish hooks. Yeah, see, I broke this bromine. And I get why did I put that the weakly line? Because remember, this one is a prochiral center. As a prochiral center, it will give me a racemic mixture, right? Plus PR radical. Why? Because here the bromine can be added dash or wedge. So that's why I get both enantiomers. I do this, I'm getting this. And that's my product. I got my two products, HBr and the allylic. Right? Now in termination, I almost like Terminator, the movie. Termination, I bring all my radicals, right? What are my radicals? I will simply with pencil here, 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 this one. Yeah, but I didn't use this one. I used this one. Yeah, we just use the ones that I used in the reaction. Bromine with bromine radical, allylic with allylic, right? The self-termination, and then the cross-termination, bromine plus the allylic. So here, bromine, fish hook, fish hook, fish hook, fish hook, fish hook, fish hook. Yeah, see my fish hooks. BR. Here. I think so. Yes. And here. Here will be here will also proximate. Is it important the stereochemistry of determination? To be honest, no. Don't worry about the stereochemistry of determination, because really these ones are not the final products. Well, except this one, right? But if it's in determination, don't worry about it. It's in the product when you guys have the propagation, that's what you have to be worried about. Okay? So for the reaction. Okay? Determination, no, because here you will form X molecules, and we don't really have to be that worried about these X molecules that are not that useful. Okay, so that was the second mechanism, I promise you, and then I'll show it to you. Let's continue now with the lecture. Let's change color. Next, this one is the mechanism, right? You see it here, the resonance structures. You can have two products, and that's exactly, so bromination alkenes is selected for allylic. Yeah, this one is my allylic position, and this one is also my allylic position. In this case, my molecule is symmetrical, so you will get the same product. But if your molecule is not symmetrical, you can get allylic bromination here and allylic bromination right there. Right? So both of them are allylic position, therefore you have as many potential products as number of allylic positions, unless your molecule is symmetrical. Like this case, this molecule is symmetrical, therefore this allylic position is equivalent to this allylic position. Great. Now, to avoid competing alkene, what is that alkene competition? And then I will tell you right here that we have the reaction. I'll open my camera right now again. Remember this particular part, this one, my initiation, that I break it into two bromines, right? What's this one? The fate of this bromine is going to this propagation, right? So that is where it goes. But what happens with this one? This one is also radical. Is this also going to react, or is going to wait for this guy to finish it? No, this is also going to react. That's the bad thing. Why? Because each bromine, they have their own reaction paths, and sometimes they might cross. So that means that this bromine might brominate the brominated product of this if they cross, right? So that is what causes a conflict of reaction. That's why you guys get polychlorination, polybromination. Why? Because if you form two radicals, two initiator radicals, right? Two Br radical, this one will start brominated. This one also brominates, and then eventually these two will encounter. If they encounter, this one will brominate something that this one already brominated. So it will be like a cross bromination, multiple bromination, and that's not something that we want. We want a monobromination, right? So that's what to do to avoid that. To avoid that, we are going to use something called NBS. NBS, here is spelled. I mean the real name, N-bromosuccinimide. N-bromosuccinimide, but normally we call it NBS. It is an initiator, is a molecule that produces a radical with the action of light. And the advantage of this molecule is that it only produces one bromine radical. Okay, so then you won't form two paths of the reaction. What happened with the other half of the reaction? The other half of the reaction is succinimide. Succinimide is stabilized by resonance. See here, 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 and also here, here, and here, right? It's stabilized by resonance. This one is a whole resonance area or surface, or let's say chain of atoms. So that's something that helps for that second radical to be stabilized. It's kind of like a inhibitor. But the important thing is that you only produce one bromine radical. So this bromine radical will only have one path of bromination. Not like the previous one where you have two bromine radicals, that they each have a path and eventually they can cross. If they cross, that's when you guys have the polybromination, right? So there is no competing addition reaction. See, there's no competing reaction. Is minimized, right, with these two, right? So that's the advantage of anytime that you guys see NBS. NBS would be another way how to say Br2. Now, is there also like an equivalent for NCLS? No. No, there is no variant for chlorine, right? Because you will say like, oh, this one is only for bromine. What about for chlorine? Is there any equivalent? I haven't really seen it. Maybe there is a chlorine version of it, but I have seen only NBS, to be honest. Maybe it should be because of the radioselectivity of bromine. That's only why succinimide is present or is used in reactivity, organic reactions, right? Good. Propagation produces the allylic radical reaction, right? So here is the initiation process. Propagation, bromine will attack a hydrogen abstraction, we'll get the allylic radical, The allylic radical will do like a halogen abstraction, reacts from forming this bromine. This bromine as a chain reaction will go back here to repeat the cycle, right? Now, in the case of asymmetric alkenes, yeah, you will form two allylic, right? Remember, that's exactly what I was telling you, that this side is allylic, but this allylic will also produce a resonance stabilized allylic reaction, right? Because you can do resonance here. You will get that. So this one will give you this product and this one will give you this product. So definitely you will say like, okay, so am I going to get a 50-50 all of them? No, of course, the tertiary allylic is favored over the primary allylic. So this one will be a slightly more a major product than this. Here it tells you like a mixture of isomer. It doesn't tell you an even, right, mixture of isomeric products. No, it tells you a mixture of isomeric products. Why? Because it is a mixture. But is it a 50-50 mixture? No, it is not a 50-50 mixture. You always produce more of the more stable radical. Is the most abundant, is the one that gets more, right, higher concentration. So normally my questions, quizzes and exams, even for the final exam, you guys will always be asked the major product, unless the question tells you all products. Yeah, in that case you have to specify, but most likely, I mean, I will ask you for major product. If there is any all products, yeah, you will want to consider even that second compound. Okay, so where do we find these radicals, or where is it important? Antioxidants, right? I'm sure that more than one person here in this room, in this class, is using like some antioxidant, like moisturizers, or maybe hyaluronic acid, or hyaluronic acid for the hair, to avoid, right, to preserve a good, right, the silkiness, right, silky, shiny, to prevent oxidation, degradation, decomposition of your hair. Even for the nails, some people, they take also some keratin, other products to prevent oxidation, maybe some moisturizers, right, creams, right, that is used for the external. Even some people, they take anti-stress. Anti-stress is antioxidant that produces stress. Women that are about to get pregnant, they also have to resist stress, because that also involves in the growth of the fetus, right? So to have a better growth of the baby, it has to be stress-free, and there are some molecules that are reduced stress molecules. So those are called antioxidants. Some of them are vitamin E. Vitamin E reduces the radical production, right? Why do you guys think that vitamin E is used in sunblock, right? Why? Because you have to apply it because it prevents the sunlight, which carries ultraviolet light, to shine or to attack your cell molecules, right? Your skin, right? Your skin, you have many molecules. If you shine them with UV light, of course, you will trigger radical reactions. How do you protect your skin from these radical reactions? By applying vitamin E. All these sunblocks and then all these, right, moisturizers against sun, they all have vitamin E. Why? Because vitamin E traps radicals. Where is it that, where this is instruction of vitamin E? Where is that protective area? Right here. That benzene ring. See, benzene ring is everywhere. And then with oxygen here, oxygen here. That is your protection. That is what protects you from the UV light. So you apply the moisturizer. Right? Right? So I have here my hand. So I apply the moisturizer. Let's have some moisturizer. Where are you? Here. Okay. I apply it. Right? So I'm protecting my skin from the sunlight. So when the UV light goes to my skin, it finds the vitamin E. So it produces radicals, but it produces radicals on my on the vitamin E, no radicals on my skin. So that's why anytime that you guys go to the beach, make sure that you apply one coat of the sunblock. Go to the ocean, go to the water, and then once you come back, make sure that you reapply more. Why? Because the vitamin E is somewhat soluble in water, so you will get it off. of course, these moisturizers are ready for that. So that's why they are kind of thick, right? Thick consistency is because they are supposed to be water resistant. But there is nothing 100% perfect. So even that 100 water resistance might be vanished, right? After few dives. I mean, when you are in the water for a long time. And protect the more sensitive area, neck, right? The face, the forehead, the arms, right? The legs, I mean, the thighs. Those are areas, your back, definitely those areas you want to protect because they are they are not really exposed to the sun that much, right? Normally the area that we exposed to the sun that much is the legs when we are wearing shorts. So our skin is a little bit thicker. So it is self-protected by the thickness of our skin. Okay, but that is the action of the sunblock. That's external. Internal, we have one protection, which is vitamin C. That's why they say always like vitamin C that you need to have citrusy citric fruits, like for example, orange, tangerines, pomelo, kiwi, right, limes, lemons, all that. So this should be part of the diet. Why? Because they are rich in vitamin C. They are highly polar. Yeah, this polar. Why? Because you have OHs, 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 so they form hydrogen bonds. That's why it is a type of antioxidant that goes inside your body because it is soluble in water. Vitamin E is hydrophobic, so it will not really dissolve in water, so you cannot eat it because it will not be transported by your blood. But vitamin C can because it's soluble in water, so it will go down the stream in your blood. So it will be a perfect antioxidant. So include vitamin C in your diet. It will prevent aging for all of us. Now, where does aging happens? Aging happens in the cell, in an organelle called, anybody knows? 3 seconds. 1, 2, 3. Yes, in the mitochondria. Mitochondria is the place where the free radicals occur, is where the respiration happens. That's where the oxygen does the process of the metabolism or the oxidation. That's where oxygen is concentrated. Therefore, the amount of free radicals that are inside is so high. Do you ever wonder why mitochondria is the only organelle that has its own membrane, right? Because nothing else has a membrane, right? The Golgi apparatus, no membrane. Lysosomes, no membranes. The only one that has membrane is the mitochondria. Mitochondria even has its own DNA. So can you ever wonder why it's a separate organelle, it's a separate cell inside of the cell? So why is that so special? Because mitochondria is responsible for the oxygen management. All the free radicals, all the things that are aging you is inside the mitochondria. So the mitochondria is in charge of that. So can you open if that membrane gets opened or ripped? So definitely all the free radicals will go out and then everything will get destroyed. Why? Because the radicals are all really aggressive. They're very reactive. Right? Okay, so that's about the introduction. I mean, more introduction, anything that I see. I like to share what all I've been learning over the years with you guys because I really want to give an application of these organic molecules because otherwise they're just going to be a bunch of carbon, hydrogen, oxygen, nitrogen with no meaning, or lines, zigzag lines, or rings with no meaning, but they do have a meaning. And then it is really a high impact in our lives. Mostly health, environment, industry, everywhere around me. Right now, I'm in my office. I'm in front of paper with dyes. Definitely, that is all organic chemistry. I look the other side. I have a metal cup. Metal cup is also has some organic chemistry. Yes, because it has some coating. You cannot just eat it. There is a coating that has a plastic coating, most likely, that makes it resistant to oxidation. Maybe special type of alloy. I turn more on the back. I have that soda can that I was showing you for the benzoate. That one also has organic chemistry inside. The sugar, sugar replacements, color, flavor, right? Can, the paint in the can, everything is organic chemistry and everything has an application that I try to share with you guys. All right, so we're almost done. So a few more slides. Then there's the radical addition of HBr. This one is the anti-Markovnikov reuse selective reaction to alkenes, right? Here in this slide, you can see that the regular HBr can be added Markovnikov, right? Markovnikov, we know, it means that the hydrogen goes to the least substituted and the Br goes to the most substituted. That's what Markovnikov says. In the anti-Markovnikov addition, you have HBr peroxide. It happens the opposite. The H goes to the most and the Br goes to the least. Why is that, right? The peroxide initiate the radical mechanism of the addition. So the peroxides are the ones that are responsible. So if we remember in the mechanism, so let's just bring back memories. Which one gets added first in the HBr? Okay, just think of it, of the mechanism, or maybe just bring your notes. Who is added first? Yes, the H. The H is added first because the H is attacked by the alkene. The alkene attacks the H and the Br leaves. That creates the carbocation on the most, right? On the most substituted carbon of the alkene. What do you think is going to happen in the HBr peroxide? Which one is going to be added first? Yes, the bromine is added first, leaving the radical on the most stable carbon. That's the difference between these two reactions, okay? Yes, you guys got it, yes. So the alkene attacks first in the to the hydrogen in the regular reaction, but in the radical is the bromine that goes in first, leaving the most stable radical. Therefore, the radical will take the hydrogen to the most substituted, okay? So let's explain that with the mechanism. Okay, so once again, let's do it. You know, you guys know that I'm gonna turn off my camera, sorry, my slides. I'm gonna do the anti-Markovnikov. It's a very long name, anti-Markovnikov addition of HBr to alkenes. You know, alkenes, I use it as initiation. How to initiate this reaction? The reaction, let's do it like that. This one with HBr peroxides produces this compound, okay? Initiation, who's gonna initiate here? Here, peroxides, right? If we go back to the slides, right? So there were three compounds that were used as initiators, halogens, peroxides, or acyl peroxides. In this case, I have only peroxide, no acyl peroxide, so I will have to use peroxide. So ROOR. With the effect of light or heat, we'll use light. This one has to break up into two ions. Sorry, not two ions. Two radicals. See? RO radical plus OR radical. Two radicals. Now, are these RO radicals inside of the, is part or is not part? No, it's not part, right? My product doesn't have any OR. So I have to continue until I find my product, something that is part of my product. So what else can I bring? I can bring the HBr. Which one is gonna go with the RO? I'm gonna break this bond. Bromine goes, this hydrogen. Remember, hydrogen is the easiest to go. So that's why the hydrogen leaves and goes to ROH plus Br radical. Now, is this Br radical part of my product? Yes. So that's the end of my initiation. Now you said, oh, professor, but here you are making a propagation step, type of propagation step. Yes, it looks like a propagation step, but only for this reaction it is needed. Why? Because the radicals I produce in my first initiation step is not part of my molecule. So that's why I have to use a second initiation step that really looks like a propagation, because this one is a radical with a neutral compound. That's a propagation, but it's needed for this reaction. Okay. Next, let's do the propagation. So I bring that radical that I just made, Br radical, and then I bring my substrate, which is this compound. So in this reaction, now I have to attack it. Now I know what you guys might be thinking, like, okay, so here I have an allylic reaction, right? An allylic position. Why is this not doing an allylic, right? Why is it going to be doing this? I mean, alkene reaction with a halogen. The reason is it really depends on the formation of the radical. Okay, so in the previous reaction, let me see if I have it here. Okay. Here, right? Very similar in my other reaction. I have a bromine with the substrate. It was adding to the allylic. Why in this reaction will you will attack the alkene and not the allylic? It's because of the substrates that you are using. In this case, you are having Br molecule. Here you don't have Br molecule. Here you guys have HBr. HBr does not recycle, does not generate a circle of radicals. In Br, in Br2, yes. That's why it follows this route. This particular path is followed by this reaction with the allylic. Why? Because I have present Br molecule. Br molecule will, with this path, will recycle. This one was, again, right, like a circular chain reaction. That is not possible here. That's why this bromine knows that there is no bromine in the system. It's only HBr. So it has to sustain the reaction somehow in a chain reaction. So that's why it won't attack it in the allylic, it will attack it to the alkene side. Okay. This one is split into two. Of course, I want to produce the most stable radical. See, what is the bromine being added? The bromine is added to the least attituted. Why? Because if I add it to the least attituted, it leaves me the radical in the most attituted. So that's the difference. That's what makes the difference between the HBr with peroxides and without peroxides. Okay, I made that compound. Now this compound, this radical that I just made, will react with my starting material, which is HBr. And here is where it will happen, the reaction. You see, I wouldn't form that product with a Br2. That's why this path goes through alkene, right? How is it called? This one is called, that step is called, let me see it. It has a special name. Addition to a pi bond. Yeah, this is called an addition to a pi bond. Addition to pi bond. And here I just have a hydrogen abstraction plus Br. And that Br, of course, it goes in a cyclic reaction, right? To that step. I don't get this that's why I don't go through the allylic. Because if I do allylic, I wouldn't get that chain reaction. Okay? And also I wouldn't get the product. Remember, that is the main goal of the mechanism. It's always like you are given a starting material and a product, and you have to explain somehow how the reaction, right? How it occurs here. Right? So next is the termination. In the case of the termination, you guys have to couple, right? All the radicals. Here I have 1, 2 radicals. Br with itself, Br with itself. This bromine with itself. And the cross termination, right? Oh, should I also make participate the RO radical? No, no, no. It's only like it's a drop of that you need. You don't really need much. It's like a catalyst. Here, 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 here. So Br, Br. I think so. 1, 2, 3, 1, 2, 3. Yeah. That's my product. So those are my termination products. And that's it for the mechanism. Do we have to know this mechanism? Yeah, please. Remember this mechanism, the halogenation mechanism, the allylic bromination mechanism, and this HBr peroxide mechanism. We also have one more, which is the polymerization that's coming in a minute. Okay, so this one is the reactions, the initiation. Okay, so here the bromine radical in theory could add to either side of the alkene, right? So it can add to this alkene or to this alkene. But if it adds to this alkene, it produces the tertiary radical. If it adds to this alkene, it will form a secondary radical. So that's why it prefers to add to the tertiary radical. Is more stable. Okay, so but it will add to this side that generates a more stable carbon radical. So it will be lower energy and a lower transition state. It will add that way. So the H will form. It will form. That's this other propagation. Sorry, the other propagation step, and then it will go back to the chain reaction. Termination, you can have different combinations for the termination, but here they're only showing one. Most of the radical in solution at any given moment will be bromine radical. So combination of them is typically a termination step. But the combination of any of the two radical constitutes termination. Yes, that's correct, right? So here they're only showing one termination step, but really is multiple, like the one that I show you on my sheets. Okay, the sheets where I was doing the mechanism, right? So next is the last one, the last portion. I know that we are eager to finish this chapter and also this course. The last one is the radical polymerization. There are polymers. I don't know if you guys have heard about the word polymers. Polymers, as the name says, is polymers, right? In the case of the poly means many. Mers mean like monomers. Monomers is like, imagine Legos. When you guys put Legos one, when you put Legos, imagine that these erasers are Legos, right? So this one will be called monomers. That one monomer. So I will call this one is called a dimer. This one is called a trimer. This one will be called a tetramer, right? This one will be called a pentamer. And you have many of them will be called a polymer, right? So you use all these building blocks. This one. Now, the way how you attach these building blocks can be done in different reactions. Maybe it can be added in an addition reaction, right? In a reaction that we have done, in chapter, in the previous chapters. It can also be done through radical reaction. There are radical polymers and also the condensation polymers, right? So that's how we call it. In the case of the radical polymers, is the cheapest and the easiest to make. Why? Because as you have noticed in the radical reactions, it's a chain reaction. So you don't really have to monitor the reaction. The reaction will by itself, it will polymerize. So you guys have a monomer. This is your monomer. You got many of the monomers. You just add an initiator, and the initiator will start putting the monomers together. It will activate it, and then each of the monomers will go like this. Sometimes you can get branches. Yes, I'm not, we cannot really deny that. You can have branches, but really that's the principle for plastic. Plastic, let me see. This one is, yes, here. Not this one. Let me see if I find something better. Here, if you go to your plastic bottles, right, to the bottom, right, I will have to move my camera really low, really high, but if you see your camera, I'll move it here. Here, there is a symbol. There is a triangle. I don't know if you guys see this triangle. And there are some initials here, PETE. That should be polyethylene, right? Polyethylene, it means that ethylene is a monomer that is used in plastic. Polyethylene, of course, means like many of those, right? Let me see another one. This water bottle, that doesn't have one. That's strange. This one doesn't have one, right? And you guys find it? No, I don't find it. That's strange. All the water bottle, all the plastic bottles are supposed to have, maybe it should be in one of the sides. Should be somewhere. Because that's the way how we recycle it. Because they look at the labels. No, this one doesn't have either. All right, well, that's the idea. Okay, that is interesting. This one, you guys cannot see it, but I do see it. It says PS. PS is polystyrene. Polystyrene. That's interesting that this one is polystyrene. Polystyrene is another polymer. This one, no, this one doesn't have. This one, it says, see, all these numbers, they have a meaning. Here, maybe you guys don't see because it's too shiny. Here, it says PP. Here, now that I'm focusing it, maybe. Yeah, maybe. Yeah, here there's a triangle. And what I read is PP. That is polypropylene. Polypropylene, yes. So what they do is like, they are used in the plastic industry to differentiate between the types of plastic, okay? So there are different type of monomers that can be used. They're normally alkenes, double bonds. And of course, if you put some other branches to the double bonds, of course, they will have a different type of property. For example, that alkene, this alkene, let's say you have two methyls, right? And two hydrogens. This plastic that you come up with this, maybe it is softer than this. And then, for example, polyvinyl chloride, that's one that has a halogen. This one is normally used for pipes. In plumbing, they use the polymer of this because it's really strong and it does not get corroded with humidity, right? So that's why they use this. Polystyrene is another one. Polystyrene is actually a very kind of difficult. It has an aromatic ring. That's the monomer of polystyrene. No, it's not this one. It's this one. Yeah. That is that's a styrene molecule. And you have four polymers of it. And what is that? These are alkenes. So you polymerize alkenes. Have you ever seen polymerizing alkynes? Not really. Only alkenes get polymerized. Okay. So the way how it's called is addition polymers. So means like one of these monomers gets added to the another one, and then to the other one, to the other one, to the other one. How does this addition happens? How that occurs? Is by radical reactions. You need an initiator, and the initiator will definitely activate a monomer. The monomer now is activated, will get another monomer. So you will be getting monomers and monomers and monomers and monomers every single time, because every monomer gets activated, and then that's how you form a chain. Now, the thickness of a particular polymer really depends on the time and also the type of monomer that you're using. For example, if you let it polymerize for about an hour, you will get a thickness that is different from a thickness that you will get after 2 hours or after 10 minutes, after 5 minutes. For example, those shopping bags, the grocery store bags, are really thin. That takes really short time. That's why plastic is so easy to make, because you don't really have to babysit it. You don't have to babysit the reaction. You don't have to do solvent extraction. You don't have to do distillation. You don't have nothing. It just is created as it is. You just get fibers and fibers of plastic. All you guys have to do is just cut, and then with the action of the heat, you can melt them and they convert it into plastic bags. It's pretty easy. That's why it's so easy to make plastic. It's so cheap. The bad thing is that this plastic, since it's only carbon-carbon bonds, it's very difficult to break. It won't degrade as easily. Once I read that a piece of a bottle of water, an empty plastic bottle of water, it takes about 100 to 200 years to decompose naturally in the environment. So that is so difficult to break. That's why these guys are so bad. Styrene is even worse. That's why in New York City, they banned the styrofoam lunch boxes, right? Or food boxes, right? So those are click. So now they use a different type of plastic. Why? Because the styling is so bad. And the bad thing, it floats in water. If it floats in water, birds, fish, they can all eat it. Turtles, right? So any type of animal can eat those plastic, and that's bad for the environment, right? So let's watch the the reaction. Now here we have the polymerization, how it occurs. You need an alkene, you need an initiator, you need the peroxide. Peroxide with the action of heat, right, will cleave into two molecules that now these two molecules that you just formed, right, so they will have to activate because they are not part of the main chain. So it will activate in the initiation an alkene. In this case, I'm using ethylene. So I'm gonna be getting PET, polyethylene. So this radical, I'm not gonna do the radical by hand because it's very similar to the mechanisms that you have done. The radical will break the alkene. Right here is a pi bond. It gets broken. It's called an addition to pi bond, and you get this new radical. Now this new radical will bring another monomer, getting a second, right? A second monomer. This one is called a dimer. This dimer will bring another monomer. Now you have a trimer. That it will come up with a fourth monomer. That's a tetramer. More, and more. So you guys will have a polymer that is going to be this long, ROR, this long, and continues all the way. That's how you make plastic. Okay, so this summation, right, of the propagations that gives the overall net reaction. So, and then everything is about time, right? The longer you let it wait, right, run the reaction, the longer the change you will have, different quality of plastic you will get. Okay, the termination step, you just terminate it with excess of the peroxide. The peroxide should cap it or seal it. That's how you end the reaction. Or you can always quench it with water. Water is a good quencher because it got oxygen, remember. Okay. Now you can have branching. Yes, there is branching. You cannot avoid it in the process and occurs with the other mechanism because you guys have branches. And here you have another CH that can be branched, right? So that's something that we cannot do. And we cannot do anything to avoid. Highly branched polyethylene forms flexible plastics, squeeze bottles, right? So those squeeze bottles, the one that I show you, this Poland Spring, Aquafina, those bottles that really make a sound. I don't have right now, but this one is not polyethylene. This one is, I'm gonna show you right now. This one is not, it's not like that flexible, right? So I wouldn't say that this one has polyethylene like low density. Okay, depends. It's a higher density. So why is it called low density and high density? Because the branches, they create pockets, right? So you have branches here, right? Let's say this one is my polymer. This one is my polymer. And then if I have branches, it will leave a pocket, empty pocket of emptiness. Another pocket here, emptiness, that cannot be occupied by anything. That decreases the density. That's why we call this low density. High density means that they are well packed. Let's say that we have chains like that, so you have a high density. Why? Because this one, everything is packed, right? The chain is packed as a sandwich, like that. But, you know, it depends on the type of plastic that you want to obtain. And branched polyethylene, right, is a brittle and rigid, right? Very rigid, like a plastic bottle cap. Yeah, they're different. Polymers with varying properties are obtained by polymerizing different types of alkenes. For example, propylene, right? Propylene will form polypropylene, right? Carpet fibers, appliances, car tires, you know, that's used for that particular monomer. Styrene, that's styrene I was telling you, television, radios, styrofoam, that's what you form with polystyrene. Vinyl chloride, that forms the PVC, right? That forms that particular compound, that particular polymer. Here you have TFE, which is Teflon, tetafluoroethylene. You have 4 fluorines. The fluorine, you know, has the special properties. You form this particular polymer, which is called Teflon. Non-stick coating for the frying pans. Yeah, those frying pans that have non-sticking surface, that's Teflon, because they are very durable, and also there is no sticking. Why? Because of the fluorine. The fluorine does not form chemical hydrogen bonds. It's very difficult to form these attraction forces uh, with grease. Why? Because the surface is very polar. CF bond. See where CF bond is highly polar. So it will be not sticking. Why? The fats, everything will not stick to the surface. Why? Because the fluorine will repel it because of the high polarity. Okay. In synthesis, now how can we use this for synthesis? It opens a lot of doors. You will see here, I will have more examples for the solve problem videos, but in this case, you guys can use this MBS reaction with many applications. For example, if you have this this alkane, you use MBS, you're going to form this alkyl halide. This alkyl halide can go through substitution, through elimination, 7A, this one is 7B. And then this alkene can do many things, can do chapter 8, and then can also produce an alkyne. And the alkyne can unleash all the chapter 9 reactions. See, you see all the applications that you can do with this reaction. We shouldn't have started with this reaction before, but since it's a different type of reaction, radical reaction, I took it to the end. Okay. Well, this particular book, the author preferred to have it in the end, but this one is the way how you can make alkyl halides from alkanes. Alkanes that we normally say that are unreactive, right? So now they come to life with a bromine or with a chlorine, and you can do different type of reaction with these alkyl halides and alkyl bromides. Okay, so that's the advantage. For example, this one is a reaction, right? So this alkane, alkene, you can have, it's a review of reaction. This is slide. You can do the anti-Markovnikov addition. MBS with light, that's how you do the allylic bromination. This is how you differentiate it. See, HBr peroxide, you do addition to alkene. MBS, that's the allylic bromination. That's how you guys are going to differentiate. Oh, why is this one attacking allylic? Why is this one attacking the alkene? It's because of the reaction sets, right? So the reagent sets. Okay? So, and then this one, you guys are going to be using it a lot. Once again, use bromination. Don't use chlorination for synthetic purposes, because that's the one that has more applications in organic chemistry. Bromination is definitely way more selective than anything, right? So I'm going to end right now. I don't want to really saturate you with a lot of lecture. It's the last chapter, kind of long, but that's all. So thank you guys for sharing with me this chapter 10 and also the entire chemistry 230 class. Thank you a lot for your patience, for always your feedback is appreciated. If you find anything that maybe I can improve, or professor, maybe they are too long, please let me know. So there is room for improvements. And then hopefully with this particular lecture, you learn more about organic chemistry, and organic chemistry is not as difficult. I mean, difficult might be, but it's not as boring, or maybe it has no applications. You found like a different taste of organic chemistry after the semester, and then you're encouraged to take organic chemistry too. All the best, my best wishes for you guys. If you're taking the next class with me, or with another professor in another institution, or maybe here the same institution, is all the best. You guys are strong with the foundation that we have in organic chemistry, and definitely you're ready for organic chemistry too. So all the best. Good luck with everything, and then I'll hope to see you soon after this class, right? So take care, and then thanks for being with me and tolerating my voice and my problems, right? My practice problems and my accent, my handwriting, my everything, all my writing. In general during this semester. Hope to see you soon. Take care, all of you.